This also.
For the
Correct advantage.
Yeah. Yes.
25. Yeah. Here now.
Yep. I've used it last week.
No, the slides are.
Yes. Yeah.
Yeah, 18 minutes. 8 plus 2. Questions really limited.
Yeah, one. Yeah, sure.
I'll ask you.
Yeah. That's what I'm here for, discussions.
Okay, we'll start with a set of 4 short talks. First, Elisabeth, she is going to tell us about FRPs.
Okay. First of all, thank you to ICTS for hosting us first for the school and now for this workshop. And also for the organizers in all the flexibility with the scheduling. After I learned that my former student friend and I were going to talk about the same thing, I switched and I will talk today about probing baryonic feedback with fast radio bursts. This is work really undertaken by Kriti Sharma, who is a fantastic final year grad student at Caltech. So she'll be applying for postdocs this fall, look out. And her formal advisor is Vikram Ravi, most an instrumentalist, who's making all these wonderful FRB samples happen. So, of course, FRBs have very rich astrophysics, and one could give a whole talk about that. But for the purpose of this short talk, I will just use them as a backlight for cosmic structures. And the idea here is that a quick burst emitted from the FRB itself will travel through plasma and then acquire a frequency-dependent arrival delay due to plasma effects. So that means that in a plot of arrival time versus frequency, the fast radio bursts will be this extended block from which we can then infer the column density of electrons between the telescope and the fast radio burst. And that is an effect, this dispersion measure is about 300 parsec per centimeter cubed over a gigaparsec sightline. Now, with this dispersion measure, we can probe cosmology and astrophysics along the line of sight. First off, the mean dispersion measure is simply the mean electron density between us and the redshift of the FRB host. So that's the simple function of cosmology parameters, line of sight integral over the electron density. The sightline to sightline variance in dispersion measures, that is really related to the clustering of baryons. and can be written as a function of the electron power spectrum. This then allows us to probe astrophysics. So here you can see now the distribution of dispersion measures as a function of host redshift. And importantly, this distribution becomes narrower as feedback strength increases. We now want to use this to probe astrophysics and, in turn, the suppression of the matter power spectrum. So here you can see, as a function of feedback strength from different hydro simulations, both the distribution of dispersion measures as a function of host redshift and the power spectrum's suppression. So as feedback gets stronger and halos, so to say, get puffier, electron power spectrum decreases and suppression of power spectrum increases. That's the effect that we are after. And practically, this will then allow us to provide a complementary probe of baryon feedback. Let's first look in a plot of mass versus redshift, what the different observational probes do. Here is the mass and redshift distribution of E-Rosetta clusters. This is about the mass and redshift range probed by different kinematics and the Azadeh effect stacks. Then we can use TSZ through the cluster YM relation. We can also look at the cross correlation between TSZ and weak lensing, which will probe in a much wider range of halo masses and redshifts, because we're now also looking at really the contributions to the overall matter power spectrum and integrated along the line of sight. This is about the sensitivity of cosmic shear in the one halo term, so probing quite a wide range of masses. And then the distribution of dispersion measures comes in there, probing really high mass, high halo masses in the lower redshift at the moment. We often get asked, why are you sensitive to such massive clusters? And that really comes back to the electron power spectrum. We can just see that here on the right, now color-coded by minimum halo mass that we include. And really, most of the contributions to the electron to the gas power spectrum come from the halo mass range of 10 to the 14 to 10 to the 15. Now, we used 114 localized FRBs. So for those, we have a host redshift and a clear localization on the sky. And here you can see them on this plot and the distribution of source redshift and dispersion measure. And then we analyze that distribution to constrain feedback. The idea here is that we use a baryonification type model, where the first ingredient, of course, is gas density profiles as a function of feedback strength. From that, we predict the gas power spectrum. And we can then connect that to the DM variance and the actual distribution function of dispersion measures. That's what we fit to the observations. That's our 114 FRBs. And in turn, we constrain feedback strengths and then can derive halo gas fractions and power spectrum suppressions. The upshot is the white hatched contours here, which are our constraints from FRBs on power spectrum suppression. And overall, we find a preference for more moderate feedback, largely consistent with current constraints from X-ray measurements in the nearby universe, and somewhat less than inferred from KSZ or TSZ. And you can also see that this is more consistent with moderate level hydro simulations, like say Simba or Bahamas, rather than extreme scenarios like the original Illustrious. One more FRB measurement of feedback that I want to highlight from Kriti's recent collection of FRB large-scale structure cross-correlations. That is now the cross-correlation between fully localized FRBs from CHIME with the ROSAT soft X-ray background. So there we measure X-ray surface brightness cross DM as a function of separation. And then again, through a baryon feedback model, can connect it to feedback strengths. Here are again our measurements with the colored area as a central region, comparing to the measurement that we would infer from our line of sight variance of dispersion measures, or very weak or strong feedback scenarios. We find that the DM X-ray correlation here is consistent with what we get from the distribution of dispersion measures, and again points towards more moderate feedback. And this really bodes well for the future. I had shown you this sensitivity plot before, and also what our current FRB constraints are. Now, in order to use this for, say, LSC cosmic shear, we're really excited about next generation FRB experiments, like a deep symptomatic array, SKA, and CORD, which will now probe feedback over a much larger mass and redshift range, and cover part of that parameter space or that feedback space that's really relevant for next generation shear. And through that, we should get much tighter constraints on power spectrum suppression. And with that, I will leave you with my conclusions, because I'm at 8 minutes. Thank you.
Thank you. Thanks, Elisabeth, for keeping the time. Questions? And may I request the next speaker to come? Questions for Elisabeth? Yes.
Me? Yeah. So I just wanted to understand, there is also the FRB and then the host galaxy, right? So when you're talking about site-to-site variance, isn't the host galaxy also, it's not just the line of sight, but the host galaxy?
Oh, of course, there is a host contribution. And in one of the many appendices of that paper, we also go through how different current models for the
Okay, thanks, Elisabeth. We'll move on to the next talk by Ayan Nanda. We'll talk about the role of mergers and environments affecting helomorphology.
So, hello. So, good morning, everyone. I am Ayan Nanda. So, first of all, I want to thank the organizers for giving me opportunity to present my work over here. So, the title of my talk is The Role of Mergers and Environments Affecting Helomorphology and Morphology-Dependent Clustering. So, this work is in collaboration with my PhD supervisor, Dr. Nishikanta Khandai, and our past postdoc in our group, Dr. Swati Gavas. So this is the brief overview of my talk. So let's just start. So we see light from galaxies, but our observation suggests that our cosmic structures is dominated by invisible matter, namely dark matter. So if we see the galaxy distribution from various redshift surveys, like in the right plot, side plot, you can see in the redshift and right ascension coordinate, the blue dots are the galaxy distributions, and the similar thing from mock surveys from in Millennium in-body simulations, the red dots. So you can see that the distribution of galaxies, so and the mock surveys from in-body simulations, so nearly identical in distinguishable structures such as this Stickman diagram and this great wall and the other cosmic structures. So what this really suggests, so galaxies closely trace the underlying dark matter distribution. So from hydrodynamical simulations also, we have found that how the different components like gas and stars are following the underlying dark matter distribution. So this is a visualization from recently the Ninja simulations from one of the boxes, 50 MPs with 640 cube. So this is the dark matter density, and this red colors are the gas surface density, and this stellar surface density. This is the left. So you can see how the stars are density is higher where the dark matter surface density is higher. So these are the places where the galaxies are forming and tracing the underlying dark matter distribution. So in our work, we are focusing on the merger aspects in the structure of dark matter halos, and why we are doing that. So to begin with, so let's see the basics of halo morphology, halo shape. So this is a typical halo identified from a simulation. So using Rockstar algorithm. So this halo is identified, has been assumed to be an ellipsoid which has three axes A, B, C, and three principal axes and eigenvectors A, B, E, C. And one can define a triaxiality parameter associated with each halo 1 minus q square by 1 minus a square, and where q and a such b by a and c by a. So one can segregate these halos into three categories: oblate, triaxial, and prolate based on this triaxiality parameters. So if we separate these halos into three categories and see their abundance, so we have shown in one of our earlier work that so the halo abundance is basically the number density of halos per unit logarithmic mean. It is related to this f of nu multiplicity function via this relation, where nu is that peak height, where is the ratio of critical over density threshold divided by the cosmic mass variance. So this nu is absorbing all the cosmology, power spectrum dependence, and growth factor. So as a result of which we plot f of nu as a function of nu. So we see that universality pattern. So, but if we separate them into three categories, we have also found that they follow an almost universal pattern. Okay. So then the naturally we have seen that next question we have asked that what how this fraction of these three halo populations they evolve over cosmic time. So what we have found that this oblate fractions, so this is in the y-axis, this is a fraction oblate, triaxial, and prolate halo fractions, and which has been plotted as a function of the same quantity parameter nu. And what we have found that these prolate fractions at high redshift is very high, and over the cosmic time it decreases, and as a result of which you can see the prolate and triaxial and oblate fraction increases. So we have asked this question that what determines this change of this structure, so change of the structure of these halos and thereby their morphology. So we have, that's why we have investigated the merger of these halos. So we have tracked them back using consistent tree code. So we have run a bunch of simulations in our Niger explicit system, out of which this red one is the one which we have we generated the merger tree catalog. So it has a quite good resolution, around 10 to the power 7.5 mass resolution. So yeah, so now we'll be focusing on the merger tree. So this is a visual representation of the merger tree of a present day cluster size halo. And so in the x-axis you can see the scale factor, and y-axis you can see the different branches of the merger tree. So this shows the hierarchical growth of a hierarchical growth of the CDM halos. So they assemble, merge together and form massive progenitors. So the lines connecting from progenitor to descendants, and So we'll be focusing on mostly the most massive progenitor, which is the dark big circles. So this is called the main branch history. Okay. So we'll see the effect of merger. So before going into the evolution of these shape parameters, so we have to so instead of scale factor and redshift, we have seen this evolution in terms of dynamical time. Why dynamical time? So because halo mergers are dynamical processes, so it is essential to study these mergers in terms of dynamical time. Otherwise, because halos mergers happening at different cosmic times, so to put them at the same at equal footing, so it is essential to study them in terms of this dynamical time, and it is defined as the time required to orbit an equilibrium dynamical system. In our case, it's an halo. So it is defined as like this, and so A merger is our reference point. So and so we are integrating per merger to A, and when A is greater than A merger, so then T dynamical is greater than 0. Other if A less than A merger, it is negative. So in units of dynamical time, we are looking at their evolution. So we have looked at the oblate halos today, triaxial halos and prolate halos today, and tracing them back, see their evolution, and we have stacked them, and and we have shown the these parameters like B by A, C by A, and triaxiality. So in different four merger bins we have shown. So what we can see that at just in the pre-merger phase, so this is the pre-merger phase. So T-merger is 0. Pre-merger phase, all halos are in the prolate regime. So as the merger happens, so the triaxiality parameter increases, and it then again decreases. So it is because the infall halo as coming into the first pericenter. So it become more bit spherical. Then it goes into the apocenter. So that's why the triaxiality parameter increases. It gets elongated. But after that, for the oblate halos in the recent merger case, we can see there is a decrease. But in the triaxial halos, we can see they are in the triaxial regime. So what drives them into this oblate, triaxial, and prolate? So we can't conclude from this plot here, but we can see that there is a trend in the post-merger phase. So there is a different evolution across these three morphologies. So like in the prolate cases, we can see across all merger bins. So they always remain prolate in the pre-merger and post-merger.
Can you wrap?
Yeah.
Because it's coming
So
out.
we have also seen the evolution of the spin angular momentum vector. So how the cosine angle changes. So with respect to the merging time. So what we have.
Ayan, maybe we should wrap up.
Okay. So we have seen the directional merging as well. So we have seen the cosine angle between the major axis and the radial vector joining them. So what we have found that the infall halos are mostly coming along the major axes, but for oblate halos we can see a slight probability to the infall halo coming along the EB axis. There is a slight probability that may be the reason for forming these oblate halos. And we have seen the tidal environment, and ultimately I want to show the large scale assembly bias. So across these three morphologies, although oblate halos are lower in fraction, but they show a large scale assembly bias, higher large scale assembly bias. So as a reason, the reason we are trying to understand, then you can see that they are younger compared to the triaxial and prolate halos, so which is consistent with the assembly bias. Yes, thank you.
Okay, thanks. Maybe the next speaker can set up and
Hello everyone, I am Vikhyat Sharma. I am a PhD student at IISER Pune working with Dr. Orko Banerjee. Today I'll present on the topic N-body simulations for LIMR cosmologies. Let me start with a very brief introduction. As everyone in the room knows that more than 80 to 85% of the matter in the universe is made up of something which we very feebly understand. We call it dark matter. There are different models of what a dark matter particle could be. It can be CDM, HDM, some axions. There might be some self-interactions in dark matter, or it could be something which we have not thought of yet. But then looking at the baryonic part of the universe, we have different particles in the baryonic parts in the standard model, and there is no reason to assume that all the dark sector has to be made up of only one kind of particle. So we in our model have a heavy particle which is CDM and a light particle which is the LIMR. LIMR stands for light but massive relics. These are hot dark matter candidates. The mass is of the order of a few electron volt, and these particles become transition from being relativistic to non-relativistic somewhere between early universe and today. Now, people have tried to put constraint on properties of these LIMR particles, but no one has looked into the non-linear scales. All the studies have been on the linear scales only, and we, using N-body simulations, want to look at that. This is then a setup of N-body simulation that exists previous to this work. We start with a code called class. We modify reps to set up a 3-fluid simulations. By 3-fluid, I mean CDM particles, standard model neutrinos, and these LIMR particles. The code PyReps is publicly available, and you can scan this for the GitHub repo. And then we modify engine, IC, and gadget, and we are all set to run 3-fluid simulations. So I'll show you the first results. This video shows the evolution from redshift 20 to redshift 0. This is for only CDM case. This is CDM plus standard model neutrinos, and this also has LIMR particles. So clearly these LIMR particles wash the structure at large scales. And individually, these LIMR particles are more efficient in clustering as compared to the standard model neutrinos, but still do not cluster as much as CDM because of their non-zero thermal velocities. Now we look at different cosmological observables using these LIMR cosmologies. We look at the power spectrum, halo mass function, mass concentration relation, and the weak lensing. We see in all the observables, we see a suppression as compared to the 2-fluid cosmology because of non-zero velocity dispersion of these LIMR particles. Now the question that we want to ask in the next thing is, consider 2 LIMR particles, one is a fermion and one is a boson. Now consider that the value of delta N effective at CMB that they have, the difference in that value is such that you cannot detect, is less than what is measurable from the current cosmological surveys, and you also cannot differentiate between those two based on linear theories like class and CAM. Is there a way to differentiate between these 2 particles using the setup that we have built? For that, we start with 3 distribution functions. We have a Fermi-Dirac particle, we have a boson, we have a Dodelson-Wittrow distribution. I'll not go into the details, but amongst the various possibilities, we see that when we fix the mass, fix the free streaming scales and omega values of these LIMR particles, varying mass and temperature, we are able to match the power spectrum across redshifts in the linear codes. So this is what the distribution functions look like. Dodelson-Wittrow, the point that I want to make is that Bose-Einstein distribution is the blue line and red line is the Fermi-Dirac. Clearly, Dodelson-Wittrow is just a renormalization of the Fermi-Dirac particle, and the number of particles in different momentum bins remains the same. Now, this is the power spectrum from class, which is a linear code. This is a total matter power spectrum. Blue line shows the ratio -1 between Bose-Einstein and Fermi-Dirac, and the green line shows the Dodelson-Wittrow and Fermi-Dirac ratio -1. Clearly, there is no difference in the power spectrum from class code, but when you run N-body simulations, this is what you see at redshift 0. There is a 2 to 3% difference. Now, when you look at the only LIMR power spectrum, this is what it is from class at redshift 0, and this is what you get from the N-body simulations at redshift 0. You see a 7 to 8% difference at small scales. Now, we want to look at, we also look at the 3D density profiles. The total density profiles look more or less the same. There is a scatter, But if you look at the only LIMR particles, the Bose-Einstein particles have clustered more into the halos as compared to the Fermi-Dirac particles, although Rudolph and Widrow show almost no difference. Now, the question that we want to ask is why so? So for that, we look at the different velocity bins and how the velocities would evolve as a function of redshift. The dashed line is, the dotted line is the unperturbed velocity, which is 1 by z if there would have been no gravitational interactions. The dashed line is the Bose-Einstein and solid line are the Fermi-Dirac. We were able to notice that at initial redshift, the average velocities of Fermi-Dirac particles was higher than that of the Bose-Einstein particles. Now let's look at the ratios because it is not very clear from that. So initially at redshift 99, Bose-Einstein particles have a lower average velocity as compared to the Fermi-Dirac particles. But at redshift 0, the velocity starts to match with each other and also with the CDM particles as seen in the last plot, which means that the particles have virialized by redshift 0. Now, we also look at the fraction of particles which have virialized as a function of redshift, starting from redshift 1.5 to redshift 0. Initially, more fraction of Bose-Einstein particles have virialized, and by redshift 0, they, like Fermi-Dirac, also try to follow them. Now, this is the last plot that I want to show. Consider a situation when Bose-Einstein particles have low velocities. Particles with low velocity will start falling into the potential wells at early redshift. So, what you expect is the time at which the Bose-Einstein particles have started virializing into the halos and Fermi-Dirac are yet to follow, you would see the most difference in the power spectrum, and then that difference would decrease by the final redshift when both of them have started virializing. Now I'll show you the plot. So this is at redshift 90, and this is from class. It would remain same throughout the redshift. That is what we wanted to have. But this is from gadget. At redshift 99, they match. As you evolve, this is at 19, this is at redshift 9, this is at redshift 2.5. Now you see at redshift 1, the difference starts becoming low and low, and this is at redshift 0.5, and this is at redshift 0, the blue line. This is what it is. So at some redshift, the difference is higher, and then it starts decreasing by the final redshift. This is a summary. These are a few references. Thank you.
Questions? Yes.
Hi, thanks for the nice talk. So I was wondering, for your Bose particles, do you also observe some solidonic cores in your simulations? Because
Sorry,
it is
what?
expected for bosons,
Yes.
LIMR bosons. So do you observe any solidonic core because it is expected to?
It is
have-
expected to.
Sorry.
Uh,
What I'm saying is, do you observe any solidonic core in your simulations in your halo?
So we do look at the halo virialize. So we look at the number of particles, LIMR particles, which are virialized into the halos, and we do see that Bose-Einstein particles start falling into the halos at earlier redshift. So around redshift 1.5 or 2, you see more Bose-Einstein particles which have fallen into the dark matter halos, but very less Fermi-Dirac particles which have started falling into the potential wells. So that is how we deduce this. Yes.
Last question before we switch.
It's going to be by Ranjini Mondol. She is going to tell us about the dark secrets of baryons. With,
Hello, hello, am I audible? Hi everyone, I'm Ranjini Mondol. I'm currently an NPDF fellow at Shaha Institute of Nuclear Physics. So today I'll talk about our recent work, Dark Secrets of Baryons, Illuminating Dark Matter Baryon Interactions using JWST data. So this work has been done in collaboration with Shorodip Dash, who was a master's student at IISc and now a grad student at Ohio State University, Abhijit Singh, who is currently in the audience and a grad student at IISc Bangalore, and Professor Ranjan Laha from IISc Bangalore. So our paper got published recently in Physical Review Letters, and this is a QR code that will point you to a short YouTube video explaining our work. So these are the brief contents of my talk. So first, I'll give a brief introduction and motivation to our work. Then I'll talk about the dark matter baryon interaction models that we are considering in our work. Then I'll show how these kind of interactions affect the formation of structures. Then I'll talk about how JWST is observing highest redshift galaxies and stars. And after that, I'll talk about what are the data that we have used for our work. And with this, we'll flash our most important results. And with this, I'll conclude my talk. So our universe isn't standard. So as humans, we are curious that what are we made up of? So we are made up of standard model particles that has 6 quarks, 6 leptons, 4 gauge bosons, and 1 Higgs. So the last century was devoted in understanding what we are made up of. But the next question that comes, that what is our universe made up of? And our universe is not standard anymore because 5% of the universe is made up of what we are made up of, and the rest are dark, that we do not know what they exactly are. And dark matter is 27% of it. We do not know what is dark matter, if that's a compact object, if that's a particle, if that's a wave. But if dark matter is a particle and it interacts with the standard model particles, then how do we catch it? So either we break it so that dark matter particles can interact and give photons as standard model particles that can be detected in the telescopes, that gives us indirect detection of dark matter, or these dark matter particles can impart recoil velocity and energy into the target materials in the direct detection experiments. So we shake it or we make it in colliders, which appears as missing momentum or missing transverse energy. Now, with upcoming cosmological surveys, we can also try to probe the nature of the dark matter through the formation of structures. And in this particular work, we are trying to probe dark matter baryon interactions using JWST telescope data. So this is a schematic Feynman diagram for the dark matter baryon interactions. And in cosmology, by baryons, we mean both electrons, positrons, or the protons, and chi is the dark matter particle. So the quantity that is relevant for us in the Boltzmann equation is the momentum transfer cross section. And for a set of Lagrangians, it reduces to a form like this, where this is a normalization constant, and V is the relative velocity between the dark matter and baryons, and N is an exponent that depends on the particular model that we have taken into consideration. And this N we have taken to be 0, which is for contact interaction, -2 for electric dipole moment-like interaction, or -4 Coulomb-like interaction. So what is the effect on the structure formation? We know that our universe is almost homogeneous, but there are small dark matter overdensities. So dark matter particles are sitting at the center of these potential wells. And in these overdense regions, baryons tend to fall. But since they are ambient radiation and they are strongly coupled to the baryons, they tend to push these baryons out of the potential well, and this gives rise to baryon acoustic oscillations. But now what happens when the dark matter interacts with the baryons? So then the pressure that is imparted into baryons by this radiation is communicated into the dark matter particles, and they tend to push these dark matter particles out of the potential well, and this shallows the potential well. And since these dark matter overdensities grow to give us the halos that host the galaxies that we see today, so if this potential well becomes shallower, then the structure formation is suppressed. Now let us look into the schematic diagram in terms of these equations. So these are the Boltzmann equation that tells us that how the dark matter overdensity and the baryon overdensity and their velocity divergences evolve. So because of dark matter baryon interaction, these terms encoded in blue, they appear, and this is a drag term that imparts, communicates pressure and momentum into the dark matter particles. And because of these terms, the structure formation for dark matter is slowed down. And this is because dark matter is not cold anymore. That is why dark matter develops the sound speed. So this is that sound speed of dark matter. So now, so JWST is doing us wonders. So it is looking at the time of the universe when the darkness turned into light. And we are looking into the formation of first stars and galaxies. So when light comes from a distant cosmological source, it redshifts according to this. And on right-hand side, along the x-axis, the wavelength is plotted, and along y-axis, the black body spectra is plotted. And this black solid line, this shows the black body spectra for the newly formed stars. And as you can see that this peaks around at UV, and when this light comes from redshift like 10 to 14 towards us, then this falls in the infrared band, which is exactly at the band which JWST observes. And with these instruments on board, JWST is observing first stars and galaxies. Now, what is the data? So the data that we are using is a UV luminosity function that tells us the differential co-moving number density of galaxies per unit magnitude interval. And as we can anticipate through chain rule, this will be sensitive to the mass distribution of the dark matter halos that will come from the cosmology, as well as how these halos contribute to the UV bright photons. So that accounts for the astrophysics. On right-hand side, we show the plot of UV luminosity function along y-axis and brightness along x-axis. This direction is brighter and this direction is dimmer. And these red points here you see are the spectroscopically conformed galaxies observed by JWST. So now this is a formula for the halo mass function we can write from excursion set principle. And this halo mass function depends on this variance. And this variance is sensitive to the matter power spectrum. Now, this is a CDM simulation, and as you can see that here we see structures of every possible scale, smallest to smallest scales. Now we can ask the question that what happens if we introduce a new cosmology that suppresses the matter power spectrum. So on left-hand side plot along x-axis, the K scale is plotted, which is inverse of length scale, and along y-axis, the matter power spectrum is plotted, and this red dotted line shows the suppression at small scales. And as you can see from WDM simulations, so there are the small scale structures are washed out. So in this work, we have considered dark matter baryon interactions. And here along x-axis, the K scale is plotted, and along y-axis, the square of the transfer function is plotted, which is the ratio between the matter power spectra with respect to the lambda CDM. And see, as you can see that the matter power spectrum for dark matter baryon interaction is suppressed because of the reason I showed. We would also expect smaller number of dark matter halos. So with this, I will just quickly flash my results. So these are the UV luminosity function plot, and this yellow line shows the UV luminosity function obtained from lambda CDM, and if we introduce dark matter baryon interaction, it gets suppressed, so it doesn't fit the data, so we get the constraint. So this green line is a constraint that we obtained from JWST, where the above is shaded and it is ruled out. And with 40 only galaxies, we got strongest constraint till date. So only for the electric dipole moment-like interactions. So with this, I conclude my talk that we put first constraints on dark matter baryon interaction from JWST and for a wide class of models. And with more data, JWST will be able to constrain different beyond the standard model interactions.
Thank you, Ranjini. Questions? Maybe we'll have one, and then after that, the poster people should line up.
So I think we've discussed this a bit before, but your constraints are derived assuming that the dark matter baryon scattering is the only extra contributor to lambda CDM. Shouldn't you fold in the astrophysical uncertainties also into your analysis?
Yeah, thank you for the question. So we have taken that into account. So obviously, as I showed, that it depends on both the halo mass function and the halo galaxy connection. And for the halo galaxy connection, we have taken the models for star formation efficiency and also the burstiness of the stars from the Thyssen zoom simulations. So they have given us some empirical models. So we have taken those models and varied the model parameters in our MCMC, and these constraints were obtained by marginalizing over those astrophysical parameters.
Thank you, Ranjini. We are running out of time. Any other discussions can be continued over lunch. So we'll move next to the poster session. So I request people to maybe line up. The first will be Hridaya, then followed by Abhijit Singh, Abhijit Talukdar, Amit Mondol.
You want the bag?
Savan Shinde, Ishika, Mehar Chawla, Navya, Jayesh, Rahul, and Sutirth. So one after the other, you will have 3 minutes. So please follow the time.
Yeah, hello. Good morning, all. So, my name is Hridaya and I'm from TIFR Mumbai. I work under Dr. Shadab. So, this is regarding our project on gravitational redshift. So, I'll straight move on to what we are doing. So, we are interested in this gravitational redshift, which is one of the direct predictions from Einstein's general theory of relativity. So basically what happens is, as the photon escapes from a gravitational potential well, its frequency decreases as it spends some amount of energy in escaping out. So the wavelength increases. So this is the redshift which is happening due to the gravitational environment from where the photon is emitting before reaching us. So if we are able to constrain this signal from a large amount of data, that is at the large scale structure, so then we will be able to constrain different parameters related to gravity, such as the matter density, the growth rate, etc. So this will basically help us in breaking degeneracies between gravity models. So this is the motivation behind this research. So the main aim of this project is to build an analytical model which we can test on real data for the measurement of this signal. Yeah. So the analytical framework that we have selected is proposed in this paper, the 2013 paper by Rupert Croft. So where they show that the average mass difference between two halo populations. So there is a massive halo population, there is a lighter mass halo population. So they have modeled this mass difference in terms of the halo matter cross correlations. So the difference in the halo matter cross correlations is somewhat the difference in the clustering strength between these populations, which we can integrate over the spherical radius to get the mass. So basically, we have modeled this mass difference into two distance regimes, the nonlinear regime by the difference in the NFW profiles between the halos, and the linear regime in terms of the linear perturbation theory. And basically, we integrate it out to large R to get the mass difference as a function of R. So then, from the Newtonian formulation, we will get the gravitational redshift difference, which is delta Zg, as a function of R using this integral, G by C from like 1 by R squared dr. So in order to validate this model, the simulations that we are using is the Sahyadri simulation. So it has a box size of 200 megaparsec and there are 8 billion particles. So this is a graph showing how the Sahyadri long range, short range and total potentials vary with the halo bias. So this is the short range is the Barner's head tree potential. Long range is the particle mesh potential we have calculated. Total is the sum of all those. Yeah. So basically, when we compare the theory and the simulation potentials, this is the curve that we get. So this is agreeing on the nonlinear regime, but the linear regime has to be modeled better than this. So this is actually an ongoing project. We are still modeling the linear regime to make the results converge better. then we can test the analytical model on real data, which is the future aim. Yeah, thank you.
Thank you, Hridaya. Please go and go to our poster for more questions. Next, we have Abhijit Singh.
Okay. Can you hear me? Okay, thank you. So I would like to begin this just by asking a question, whether dark matter can be made up of stellar black holes formed by the death of the stars. The answer is obviously no. Why is this so? In my opinion, the answer was put in the best possible words by Irshad Kamil when he told us that dark matter was present when nothing else was present. I mean, when stars and galaxies did not even form, dark matter was present in more or less the same abundance as it is today. So those black holes are ruled out. But what if black holes formed very early in the universe? That's a reasonable hypothesis, and those black holes go by the name of primordial black holes. And there are various models that tell us that you can form those black holes in abundance that's required to explain all or at least some part of the dark matter. And now we want to test this hypothesis. Now there are various ways of doing that depending upon what is the mass of your candidate black holes that you think may act as dark matter. So one way that we employ in our work is the following, that if dark matter is made of primordial black holes, now these primordial black holes will emit Hawking radiation. And then this Hawking radiation will escape the radiation will go and interact with the neutral hydrogen in the intergalactic medium, and it will raise the temperature of that neutral hydrogen gas. Now what you do is you go and you measure the temperature of the intergalactic medium gas. Now two things can happen. One is that if you find that the temperature of the intergalactic medium gas is actually higher than what you expect considering all other astrophysical sources, then you can ask the question whether that extra temperature is due to the existence of primordial black holes as dark matter which are evaporating. Of course, this is not the route that we took. We did not find an extra heated IgM temperature. Otherwise, I would have been giving an invited talk, not a 3-minute flash talk. But what we found is that the IgM temperature is consistent with the astrophysical heating. But then what you can do is you can constrain the abundance of primordial black holes as dark matter. You can say, okay, the total fraction of dark matter that can be composed of evaporating primordial black holes can't be more than a certain number. And that is what we do. On the horizontal axis, you have the mass of the primordial black holes. On the vertical axis, you have the fraction of the dark matter that can be composed of black holes of the corresponding mass. And the shaded regions are ruled out. And it turns out that this method is, of course, not state of the art. As you can see that there are other methods that are equally good or some better, but it's a complementary way. Yeah, that's all. Thank you. We do this for spinning and non-spinning black holes as well. How you measure the temperature of the intergalactic medium, which black holes Hawking evaporate, you can come and chat to me about these things or any other things you want to. Thank you.
Thank you, Abhijit. We'll go to the next Abhijit. Talukdar.
Wait.
Yeah, hello everyone. I am Abhijit Talukdar, PhD student in the Department of Physics, Guwahati University. I am working under my supervisor, Dr. Sanjeev Kalita and Dr. Shadab. So in this work, we have tried to study the cosmological perturbation in the FR gravity scenario, which is a modified gravity theory. So the standard model of cosmology, which is lambda CDM, it is plagued by many problems like the coincidence problem, the cosmological constant problem, and obviously the occurrence of cosmological singularity. So that's why here I want to go to a different theory of gravity, which is FR theory of gravity, and that is implemented here. So Einstein-Hilbert action, where the Ricci scalar is it is replaced by a more general function of Ricci scalar, which is non-linear. So when we apply this kind of changes, there are some additional degrees of freedom will be coming in the picture, apart from the G mu nu field. And those mediates as fifth force, scalar fifth force, and they enhance the structure formation. For this, we have considered a model for the Lagrangian that reduces to general relativistic scenario if we go to high redshift. And when we apply the changes, so what happens? Our universe's evolution actually goes through a standard matter era, and then it is followed by a non-GR phase, where the matter density perturbation get enhanced from the general relativistic scenario. So it essentially affects the modified growth rate and finally the power spectrum. So what here you're looking at is we have translated the theoretical matter power spectrum to galaxy spectrum multiples and compared the modified gravity and lambda CDM scenario. Modified gravity evolution, as you can see, it is scale dependent growth, and towards the smaller scale, there will be enhancement. And if we just look at so this is just a comparison of DESI power spectrum data from the year one and our theoretical models. And obviously there is an agreement with some of the model parameters of our model. Since we have seen that, so what we are expecting now from the future the surveys that will be available. So we are quite optimistic that this kind of surveys will be able to give us much better constraint on modified gravity models, because our theoretical model is ready to compare with it. And thank you.
Thank you, Abhijit. Let's move on to the next speaker, Amit Mondol.
Hello everyone, I'm Amit Mondol, a PhD student in Department of Physics, Viswabharati University. The title of my presentation is Probing the Spatial and Velocity Anisotropy Parameter in Stellar Halos from Aquarius Simulation. Let's first discuss why stellar halos are important. Stellar halos are important but most overlooked component of a galaxy. It extends far beyond the luminous boundary of a galaxy. It extends roughly a few hundreds of kiloparsec from the center of the halo. Although the 1% of the stellar mass of a galaxy resides in the stellar halo, it's quite informative part of a galaxy, because stellar halos are the fossil record of the assembly history of the host galaxy. The substructure which are found in the stellar halos are the fossil. There are two kinds of substructure are found in the stellar halo. One is diffuse substructure, other is bound satellite. These are the diffuse substructure, bound satellite. Diffuse substructure and bound satellites have different formation origin. Diffuse substructure produced due to the tidal disruption of some accreted subsystems by the host galaxy, and the bound satellites are originated due to the gravitational capture of some low mass galaxies or some globular clusters. The main question addressed in this work is, can the spatial and velocity anisotropy parameter of a stellar halo can be used to identify the assembly history of a galaxy? We use 5 mock stellar halos from Aquarius cosmological simulation, which all are having Milky Way dark matter halo mass, roughly 10 to the power 12 solar mass. Here we use 2 probes. One is spatial anisotropy, and which is an information theoretic measure, and the velocity anisotropy parameter can be calculated by these things. The investigated aspects in my analysis is spatial and velocity anisotropy parameters of the original mock halos, and after removing the bound satellites, how it behaves. Actually, it's radial profiles, how it behaves, and comparison with their sphericalized version of stellar halo. And we also use, we also show the impact of excluding the dense satellites. The key findings in my work is the bound satellites are primarily the source of anisotropy in the stellar halo. after removing them, most of the anisotropy vanishes, and also we see that the velocity anisotropy parameter traces some kinematic signature like the accretion events in the stellar halo. And here we use 5 stellar halos having Milky Way dark matter halo mass, although they have different trends we find in all the profile, so that it shows the diversity of the stellar halos. And finally, we can say that the spatial and velocity anisotropy parameter together probe the internal structure and the assembly history of a stellar halo. Thank you.
Thank you. Let's move on to the next one. Shinde.
Hello, so hi everyone. So I will be talking about properties of dark matter, halos in interacting dark matter universes. So I'm working with Professor Jasjit Singh Bagla at IISc Mohali. So when we say dark matter is interacting, what you do is that you go on adding energy in the central region of a dark matter halo. So when you go on and add energy, your particles get energy, they start moving out. And as they move out, you form a core. Then when the core is sufficiently large and you have a lower density, your negative specific heat kicks in and you go into your core collapse regime. So interacting dark matter can give you a family of density profiles. So the one we are talking about over here is that you can consider different kinds of interaction. So one we are considering in over here is basically the 2 dark matter particles interacting in a IUCAA potential. So when you go on and study IUCAA potential in Born regime, you get something like a differential cross section like this. Then when you integrate it over like with some kernel and over all thetas, you get basically the differential, you get the scattering cross section. Now we go on implementing this in n-body codes like Gadget. So currently here I am using the Open Gadget version. So so we are considering a velocity dependent cross section, and it is motivated from the observation because for the larger velocities or larger mass halos, you expect your cross section to be a smaller, and for the dwarf galaxy, you expect your cross section to be larger. So that's the basic motivation behind like the velocity dependence of the cross section. So so what we go on, we implement this, and we are trying to study how so this work is still in progress, and these are the preliminary results. So when you study interacting cross section, this omega parameter over here can relate to your what kind of model you are studying. When I say what kind of model, I say like this omega parameter is basically the ratio of your intermediator, which is you have dark matter particle interacting through some mediator, that mediator mass and the dark matter mass times the velocity. So what we are doing over here, we are varying the different omega parameters and trying to ask the question like which omega parameter is varied and what kind of mediator does it corresponds to. Currently, like as I was discussing with Dr. Orko, we found that this simulation are just for a single zoom in simulation, a single halo. The next progress of this simulation is that we are going to consider different halos and stack the results. So the results will be better from this. And we found out that the virial velocity is something that's kind of comes out to be a better performing. There's no much difference in the halo subhalo mass function. So these are the subhalo population. The next question that we are trying to ask is like, is there any inherent mass dependence? So what we do is basically so we consider a median mass and distribute like how the halos less than the median mass are distributed in a halo and how the greater than the median mass are distributed. So yeah, this study is still in progress and we expect to get these results to be better. Yeah, thank you.
Thank you. On to Ishika.
Yeah, hello everyone. My name is Ishika. I work with Professor Orko Banerjee and I'm at IISc Pune. So I'll be presenting our work towards modeling the KNN CDFs of bias tracers via hybrid Lagrangian bias framework. So as some of you might know that KNN CDFs are basically a class of higher order statistics, which are sensitive to all endpoint special correlations. And there have been various applications where we have shown that KNN CDFs provide much more robust signal to noise ratio. But in order to utilize the statistical gains provided by the KNN CDFs to do cosmology, we need to be able to model them to basically provide cosmological constraints. So this work is basically towards that direction. So first of all, the KNN CDFs are basically concerned with the CDF of distances to the kth nearest neighbor data point. And we can write out the prediction for the KNN CDFs given an underlying field by simply using the Poisson formula. The way we model them is via hybrid Lagrangian bias expansion. So the Lagrangian bias expansion is basically a relation between the proto-tracer distribution and the linear matter density and traceless tidal tensor. This functional dependence more systematically is expanded as a bias expansion where the operators are constructed out of these two quantities. And the coefficients are basically known as the bias parameters, which are basically determined by the data that we are fitting. And the key to hybrid framework is that in order to do the advection to the late times, we use the n-body simulations and obtain the late time tracer field. And once we have that, we can basically fit our model to the data and get the best fit bias parameters. Now, we also need to account for the redshift space distortions. So these are basically distortion to galaxy position caused by the line of sight velocity of the galaxies. So they basically affect the distribution in two regimes too differently. So at larger scales, there is a effect known as Kaiser effect, which causes the squashing of the distribution, whereas on smaller scales, because of virial motion of satellites along the central halo, it causes an elongation kind of effect. So we model the Kaiser effect by simply a displacement of the tracer position depending upon the velocity. And the FOG effect is typically modeled as a convolution of the centrally distorted field with a kernel, the width of which is determined by the velocity dispersion. So we have two free effective parameters in the FOG. One is the fraction of satellites and lambda FOG. So this picture simply shows one example of how this field advection takes place. You have a field at some initial Lagrangian coordinates. You do the advection to late time and then further a central distortion. So this is just showing one example of that. So we have done analysis for halos as well as galaxies, but in the interest of time, I'll just show the results for galaxies. So the main takeaway is that we are able to model the KNN CDFs across the scales which are not shaded in red. And also like the best fit parameters that we inferred from the KNN CDFs are also consistent with the power spectrum, which we expect them to be. And we have some current Fisher analysis also, which tells us that the bias parameters are much more constrained using the KNN CDFs, and I'll be happy to talk about that. So yeah, thank you.
Thanks, Ishika. The next speaker, Mohr.
Hello, everyone. So I'll be talking about testing the impact of galaxy intrinsic alignments on non-Gaussian weak lensing summary statistics for FFR and NDGP modified gravity. This was done by me under the supervision of Dr. Christopher Davies and Professor Joseph Mohr. So, well, weak lensing, galaxy weak lensing specifically, is when you have light traveling from faraway galaxies and it is perturbed by intervening gravitational potentials of the large-scale structure, and that causes distortions to these shapes of the galaxies. These distortions can be quantified in terms of shear and convergence, and there are some very nice properties of weak lensing which make it a great probe of modified gravity. So it's not a biased tracer of matter, it is sensitive to the growth of structure, and it is also sensitive to the gravitational potentials that govern deflection of light, shine phi, which make it a great modified gravity probe. But traditional weak lensing analysis actually use two-point correlation functions or two-point statistics in general. I mean, I have two maps on the screen right now. They are both from Coles and Chiak 2000. As you can see, the first map looks like a clustering simulation. There are web-like features. The second one looks like a noise map. but they both have the exact same power spectrum. So there must be some information in these maps which is not captured by this power spectrum, because the power spectrum is the same, but the maps look very different. So it turns out that there is extra information in non-Gaussian, like in higher order moments of these density fields. Those higher order moment information can be captured by these non-Gaussian statistics. So I've worked with 6 statistics in this work: full convergence PTFs, angular power spectra, which is 2-point, convergence, extrema distributions, peaks and minima. Then I've worked with void statistics as well. So it turns out that there are, of course, challenges in doing weak lensing surveys, and galaxy intrinsic alignments are a major systematic that we have to deal with. This systematic has only been studied in the context of 2-point statistics generally. There are some cases in which people have extended it to certain high order statistics. So in this work, I have essentially tried to test the impact of this systematic on these higher order statistics. And we do that by forward modeling the intrinsic alignment signal directly from the simulated matter over density maps. So just to give a brief results. So on the left-hand side, I have the predictions of summary statistics using Gaussian process regressors, which are trained on the simulation data. And each column essentially varies one cosmological or modified gravity parameter. And each row shows you the fractional difference with and without intrinsic alignments for each summary statistic. So as you can see, varying omega m or S8 or small h really causes a lot of change in the intrinsic alignment induced bias, but varying the modified gravity parameters doesn't really change it a lot. So that is one main conclusion in our paper, that change in modified gravity strength or model doesn't really change the intrinsic alignment bias by a lot. We also perform full MCMC, and as you can see, when you do not model intrinsic alignments for high order statistics as well, you have a lot of, like the posteriors are completely disjoint and there are huge biases. Also, omega m and S8 are always underestimated when intrinsic alignments are unmodeled, which is quite interesting in the sense of the S8 tension. So that's something that I would love to talk about, but I don't have enough time over here. So I'll just leave you with my main conclusions. The magnitude of IA-induced biases is largely insensitive to the choice or strength of the modified gravity model at the level of data vectors for most statistics. We find minimal biases when I is consistently modeled and no extra parameters included. S8 and omega m are always underestimated when I is ignored. Void statistics put the tightest constraints on modified gravity, and voids are also, I'll actually leave the last point for the poster. So thanks a lot. Thank you.
Thank you. Next we have Navya.
Hi everyone, I'm Navya and my poster is on my master's thesis project, which was completed at TIFR under the very patient guidance of Professor Subha and Shadab. Do black holes care about their environment or neighborhood? That is essentially the main question we are asking. In this work, we use multi-wavelength data and a stellar mass complete sample to investigate whether environment independently influences agent triggering or whether it affects the black hole accretion process itself. So our main parent galaxy sample is taken from GAMA, which is the Galaxy and Mass Assembly Survey. It is a low redshift, highly complete spectroscopic survey, which provides us with reliable redshifts and photometry for about 300,000 galaxies. So in this work, we restrict our sample to the overlapping footprint of Gamma, EFETs, DAISY Legacy, DAISY DR1, and GALEX. The figure on the left shows the distribution of DAISY, EFETs, and gamma sources in the RA-DEC plane. And the table below here essentially describes all the data sets that we have used and what their key traces are. And to obtain robust galaxy properties for our sample, we perform SED fitting using SIGAL, which is a code investigating galaxy emission. It is an energy balance SED tool. The figure on the right shows stellar mass and redshift distribution for our gamma EFITS matched sample. As you can see, as we go higher in redshift, our sample becomes dominated by higher stellar mass galaxies, which leads to an observational selection effect. So the red curve here is essentially our stellar mass completeness limit, and we include all the galaxies that lie above this limit. And we also identify AGNs using 4 different independent methods, which are X-ray, WISE, BPT, and broadline AGNs. So in this work, we introduce this parameter delta rank, which is a novel method for isolating environmental effects. And I'll show you one of our key results. So on the x-axis, we have the delta rank parameter. Lower values essentially means that you're in an underdense environment, and the higher values means that you're in a very dense environment. And the y-axis are AGN fractions for 3 different classes of AGNs. The case with X-ray agents is particularly interesting because, as you can see, that as you go from low delta values to higher delta rank values, the X-ray agent fraction, it increases about 50%. And this is shown for 2 different galaxy populations, which are star forming and quiescent. So the main takeaway is that environment does enhance agent activity, specifically for the X-ray detected population. Thank you.
Jayesh, next.
Hello, all, I'm Jayesh. I'm a PhD scholar at Manipal, and I'm working under Dr. Surajit Paul. So, as we all know that subhalos evolve in highly dynamical environments. So, we see that mergers and tidal stripping is very common over there, and it's very difficult to track them in the highly dense regions. So, to solve that, we propose a cooperative game theoretic framework where we define a utility function. And after identifying the local lower densities, we let the subhalos compete against each other for the particle association. So instead of cutting the structures from outside in, we try to grow the subhalos from inside out over here. So we are much more able to map the mergers and other dynamical environments much more better. Sorry. So one of the results that we found over there, it's very well known in the literature that subfind prefers to find the very compact cores of the identified subhalos. But over here, no matter how dynamical the environment is, we are consistently able to detect some broader density distribution. That means the subhalos still maintain their diffused layers even during the merger activity or any other tidal stripping event. So yeah, this is just an example. We ran our subhalo find over a halo of 10⁻⁴, and the other plot is just a subhalo reconstruction where the radius is square root of number of dark matter particles of each halo, normalized by the central subhalo over here. So yeah, thanks.
Thank you, Jayesh. Move on to the next speaker, Rahul Shah.
Yeah, so I want to discuss how, So I want to discuss how AI and machine learning can enable model independent cosmological analysis. So an important problem is to reconstruct cosmological quantities without assuming any cosmological model. And machine learning is a very powerful non-parametric tool for this purpose. However, before we use this, we need to validate what it learns before trusting its predictions for cosmological inference. So we demonstrate this with Ladder. So Ladder is a LSTM-based deep learning framework, which is trained on the Pantheon supernovae dataset. So instead of training on individual data points, it learns on local covariance-aware chunks of the data. So the network is able to predict not just mean values, but also its corresponding uncertainties. But predictive performance is not enough. So we did some physical validity tests on the reconstruction, namely, I'm already out of time. So namely, whether the reconstruction is smooth, whether it's monotonic, and how robust it is to the injection of noise. So once you calibrate ladder, it opens up scope for a number of cosmological applications. One of them is to check for consistency between supernovae and bow distance measures. Another is to calibrate high redshift data sets for cosmology such as gamma ray bursts. And also it can be used as a model independent mock data generator for upcoming supernovae and gravitational wave observations. So in cosmology, assumptions are made explicitly in the form of models, likelihoods, priors, etc. Machine learning does not remove those assumptions. It simply hides those assumptions behind model architectures, hyperparameters, and loss functions. So the lesson is not that AI replaces physics. The lesson is physical validations becomes more important and not less when you use machine learning applications in cosmological problems. So Ladder is open source and publicly available, so I invite you to explore it. These are my other research interests, and I'd be happy to discuss them at my poster. Thank you.
So much. Yeah. Let's go on to the last speaker, Sutirth.
Hello. So hi everyone, I am Sutirtha Mukherjee, and I'll be talking very briefly about the data-driven Milky Way science with a contiguous and homogeneous 6-dimensional phase space catalog that we have constructed with a collaboration with Amok Srivastav and Professor Subha Majumdar from TIFR Mumbai. So we made an attempt to carefully and systematically combine all the 16 and 14 surveys and 20 parent catalogs with an aim to get a precise line of sight distances and velocities as possible, and combining with a Gaia astrometry so that we have a complete 6-dimensional phase space catalog available for the Milky Way science. And so there are different challenges that we have encountered. First is that each survey will have some systematic biases associated with it. And for distances, we will be using Gaia astrometric parallaxes. So Gaia has like, after 10 kpc, Gaia parallaxes distances are not that much reliable enough. So despite keeping all of these things in mind, we homogenized the entire catalog, and we had a huge sample subtracers, which is like 1.8 billion subtracers, and we narrowed it down without compromising with the quality, and we have almost for 23 million stars in the final homogenized catalog, and this is we will be making it public. And so because we'll be combining different surveys, there can be two different cases that we might encounter. One is we may have one single stars coming from different measurements of the stars coming from a single survey, or a single star can have measurements coming from different surveys as well across all the surveys. So for two different routes, we have some kind of rescaling factors that we have to multiply with each of the errors of radial velocity. So let's say we are talking about the radial velocities. So for duplicate measurements, we have we will be computing all the pairwise differences, and we'll be getting the normalization factor or rescaling factor. And for different measurements coming from cross surveys, we'll be using something known as tri-corner hat method to have some rescaling factors. And after multiplying, we will be homogenizing all the errors and uniformly. And then after, we will be doing some 0-point correction with respect to Gaia, because Gaia is a dense catalog. So we'll be using all the stellar parameters of all the stars and do some weighted least square feet. And after that, we have lots of, so we have to merge all the individual measurements coming from the surveys. And so we have to aggregate all the measurements coming from each surveys. And after that, we'll be combining all the measurements coming from cross surveys. And these are our main results that, so before merging step, we can see that there is a sparse distribution of all the radial velocity uncertainties. And after merging, we have homogenized uncertainties of radial velocities, which is piling around 1.8 kilometer per second. And for distances, we can see that if we in the y-axis we have the relative uncertainty, which shows better measurements for Gaia parallaxes, and after the 20 kpc we have better measurements just coming from spectrophotometric parallaxes or spectrophotometric distances. So this is a cartoon which basically shows that how the it's a cartoon which basically shows that how when we are dealing with data, how the entire data set changes. So one can have just, repeated measurements coming from a single survey. And obviously what science we can do, Subha can tell, he will have a talk and he could talk more about it, and meet me in the poster. We can also talk, discuss something about it. And this is the mall projection that we have seen in the concurrence of mega survey posters. So yeah, this is coming from our work only. Yeah, thank you.
Thank you. Thank you. So let's thank all the speakers of this session and the poster presenters as well. Posters will be available for display and people will be around them during the tea breaks. Okay. So we'll meet back at 2:30 after lunch. Thank you. Lunch is addressing.